Perfect. Cool. Well, thanks for being willing to present, John.
Yeah, no worries. This is nothing long. It's actually only a few lines of code to actually make everything happen, but it does everything, or it does what we need it to right now.
Nice.
Yeah.
Cool.
Somehow I would think that's a very positive statement. It only takes a few lines of code to do everything. You want to
Well,
do, right? Like this is actually good.
Under the hood, there's a little bit more. Yeah, so I've been slowly working on the processing of the time series data, and I've gotten now just to processing the IP of a raw time series.
Nice.
You can throw 100% or 50% through the cycle, whatever. But yeah, it's now, and I've implemented your guys', I guess, the mapping kind of technique, so that you're not actually just calling all these functions, you know, to stack this and then window this. It's just, if you look down by 57 here, that one line will take your raw data series and transform it into a decay.
That's right.
One little motion. So yeah, I kind of set it up here so that, yeah, if you're, say you do have a whole bunch, you need to batch do it, and you want to play with your filter a little bit, see what your perfect settings are, that you have access to all that data so you can kind of see it. So we start off with your raw time series. Unfortunately, this is a really good signal, so I can't really show how much these things affect. But,
so,
yeah.
Okay, so what is the base frequency? Is that 8 seconds?
This will be a base frequency of, or the 2-second time base.
2 seconds.
Yeah. Yeah, so this is pretty much just outlines the steps of what the code is doing. It's taking the time series, and then it's using the filter kernel here, which is the green dot plot there. And that's essentially what your filter kernel looks like. And then beside it is the frequency response. So you can see when you use the tapered window, it's more like a low pass filter sense.
Okay, can you go a little like slowly and step by? Because
you got questions like, yeah.
Yeah, so what do you mean that like the green one is the filters? Is that
it's the filter kernel.
Filter kernel.
Okay.
So it's a convolution between your time. So what the filter kernel is it's like a moving average filter.
Right.
So each one of these, I guess, I call them caps, but these points is kind of like a weight for when you do the multiplication through. And then so your end and your beginning cycles are going to be weighted a lot less because they're kind of the starting up, power starting again.
I see.
So, but some location are double or like one location is there, the one on the top, one on the bottom is like one positive, one negative, or?
Can you try that again, Dequan? You sort of cut out there.
Those weights are like at one particular location, they're like one positive number, one negative number that's double valued.
Sorry.
Let me see if I'm understanding your question, Dequan. So the filter kernel, like there are positive and negative values, right?
That's for linear drift removal.
Okay.
Okay, okay, all right. Yeah, well, I don't understand, like just there's some positive and some negative values at the same, sometimes it can be at both positive and negative same location, or?
Okay, John, maybe just, you're gonna have to start right from scratch here, right? Because none of these make a lot of sense just to, just to make sure that we're all like either in frequency or time, and that we're working with either the whole data set or whether we're just working with one portion, and what is actually being to what is the taper actually being applied. Just assume we don't know anything, which will put you just about right.
All right, cool. All right, so we'll start right from the beginning here. So what the Halverson stacking technique does is it takes that top signal and uses all the data, and it breaks it into each of its half cycles, or half periods, I should say. And it forms a matrix so that every column is one of the half cycles, where the filter kernel is just your vector with all these values, so that when you do the multiplication, it's essentially doing like a moving average filter through. And then having the alternating positive and negatives helps remove the linear drift.
But that's a convolution. It's not a multiplication, right? Like you're convoluting half period of, so one, like a.
It works in the sense that you're convolving it with this filter kernel, yeah. But
so
you can operate it as a multiplication.
Right. So that's so you take one on and off.
Yeah.
That's a half period.
Yeah.
Then you convolute that with this. So your half period have 4T samples, am I right? Like that's at 0 to 40, is that?
The samples will be 600 samples for a half period. Or for a half period at a 2-second time base at 150 samples per second.
Right.
Is the sample.
So that's what's shown in the bottom left.
That's what's showing at the bottom one, yeah. So that's your result after your convolution.
So if you took your matrix, you take first half cycle,
Yeah.
okay, and you put that into a column, right?
Yeah.
So there's 600 points or whatever.
In this case, 600 points.
600 points, right? And then you take the next half step, reverse it in time.
Yeah.
Right? So that, well, not reverse in time, but reverse in polarity.
Polarity, yeah, sorry.
So it also kind of looks, right?
Yeah.
And then you keep doing that for however many that you've got. Okay.
And then that's how many points that'll be in your filter kernel, or how many stacks are in, or how many half stacks.
Right. Okay.
Sorry, stack is a half period. Sorry.
Yeah. Okay. So we're fine up to there. Okay. And now you've got this waking that comes out like this, down like this, right? So it's plus, minus, minus.
Yeah.
And then you're just going to, each of these gets, so this number here gets multiplied in that whole.
By that one, yeah.
And this number here gets multiplied into here.
That one.
Blah, 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 blah. So there's kind of like, an amplitude would be like that. So this would be positive for every second one, and then negative for
every other one.
For every other.
Yeah. Yeah.
Okay?
Yeah. And yeah, so the Helverson technique doesn't really do these taperings on the ends here. Your brute stack force is more like so this has been the standard way that most IP has been calculated from your instruments.
Wait.
Like that.
Excuse me. Hold on.
Yeah.
I'm missing clarity. So if you said that in your matrix here, you take the first half.
First half. Yeah.
Cycle. Okay, so that one.
Yeah.
Awesome. And then the second one would be negative, but you're flipping it in polarity.
But that's flipping it using the negative on the filter kernel there. Yeah. Oh yeah, you don't flip it before you're like when you're building the matrix, you don't flip the polarity.
So this guy's actually he's just being brought in, kind of as it were.
Yeah.
Right?
Oh, sorry. Yeah, I said it the other way, didn't I? Sorry.
So you're just bringing these half stacks in, and then you do plus minus, and average up. Okay.
Yeah. Sorry for.
No.
Makes most sense though.
Yeah. And so this has been the standard way for most instrumentation to output it is just this brute stack, and it's just got a little taper on the end there, just for the sake of beginning and end cycles. But as we see the filter response, you're actually passing a lot of that low frequency, whereas the other one, you can start by tapering the corners, you can start, removing some parasitic data, or I guess smoothing in a sense as well.
High. The other one that was acting as a.
It's a low pass.
As a low pass.
Yeah. So I guess we'll just show that difference. Yes, this organization.
That second diagram on the right-hand side in the second one, that was the response function. That's frequency.
That's the frequency response of that filter. So you can see when you start tapering the sides a lot.
And are those actually in cycles per second?
Those would be, or the bottom values are just bins. I didn't change it.
Okay.
I was just lazy, sorry.
Okay.
But if you use one, it's like up to, I think it's spans 75 hertz when you have 150 samples per second.
150.
Somewhere up there, like 75. would be your corner frequency.
Is that the usual sampling rate?
For ours is that's our sampling. So we're working on 200 here right now. Yeah, for IP we don't really keep it that high, whereas EM will use like the 20,000. Right.
And also 2 seconds seems like not very long. Is that like a usual? Like because like that's a half period, right?
Yeah.
I think I thought 8 second, like at the full period, 8 seconds is the usual IP.
We've used 2 seconds mostly. Most of the requests is 2 seconds. In the basin, it's mostly been 1 second. Yeah, we've been moving away from that because that's definitely not enough. I think, depending on where you are, but it's been seeming that you've got to have a little bit of a trade-off by acquiring the data. You start going with 4 seconds, you're starting to add a lot of time onto your survey, and that's, yeah, clients sometimes don't like to pay more, even though it's going to give a bit more.
So what was wrong with having a low-pass filter?
Nothing. Unfortunately, this data set doesn't have any bad noise in it, but you would notice that if you had, you could start cleaning up a lot of the noise in the stack if you start playing around with the filter, changing its frequency response to something that's desired.
Okay, so just to make sure, like the first one is raw data.
Yeah.
The second, the green one is the filters, Albertson filters.
Yeah.
And after that, you got the blue one.
And so this is the result.
So that's the stacked.
That is the stack. So that's after you've done the
That's the stacked response. And then
which one is the result?
blue one.
The blue one right here.
Blue one, okay.
Bottom corner.
Right. And then what is the purple?
The purple, the magenta. Yeah, that is the
Magenta.
frequency response of the filter.
So the higher the value of this curve, the more you let that frequency pass.
Exactly.
And so the low frequency is on the left and the high frequency on the right, right?
Yeah.
Okay.
But notice that the low frequency is at 0, and then we're going negative.
Yeah, so like the low frequency at 0 is busy. So I guess it's a log.
So it's passing that quarter hertz frequency or that 8 hertz frequency.
So I guess it's a log, like the Y scale is like log, so at 1 is
Oh yeah, it's log.
So at basically 0 means everything is passing, and -8 is basically you temper it by like 10 to the power minus 8.
Yeah.
So that's 17 hertz. Is that a hertz?
Oh no, that's bins. Yeah, I made this up on the bus. Sorry.
Oh, I see. So it's
I just wanted to add in more so that we could see.
right,
stuff, yeah.
right.
Yeah, it's just bins.
But like, do you have an idea about like if you actually convert that to a hertz?
Yeah,
Like,
I
do
think
you have an idea?
it
about,
would
like,
span from 0 to 75 hertz.
75.
75 hertz, yeah.
And the final one is the decay curve.
And the final is the decay.
So 2000 to.
So that's 2,000. That's in milliseconds. So that's your whole off time.
That's basically 2 seconds, right?
2 seconds on your off time, yeah. The 4 second half period.
2 seconds on, 2 seconds off.
So it's still the 8 second you were talking. So it's like 2 seconds. So like it's 2 seconds on.
Yeah.
2 seconds off. 2 seconds on.
Negative
and 2 seconds off. So that's what SOG is called, like the 8 second cycle, because like the full cycle, and negative is 8 seconds.
So I see. Your period is 8 seconds.
Period is 8 seconds, yeah.
Right.
So it's time there, yeah.
0.1.
Yeah, we refer to time base as 2 seconds.
Which is
That doesn't really make sense if you're looking at a period. But
I see. Just different.
Yeah.
So that 2 seconds is basically 0 off time, am I right?
0. There's a 20-second delay. So like, yeah, it's not quite at 0.
I'm a little
Okay,
confused
so-
about what do you mean the 20-second delay?
Oh, okay. So you just like EM is you got your turn off time.
Right. I
This is kind of the equivalent.
that's a ramp off.
There's a little bit of a ramp off. So it goes to about 2 seconds and then it stops. And then we just have a little 20 milliseconds before we start calculating the decay.
The 20 milliseconds is the delay.
Oh,
right?
yeah.
Milliseconds. I believe that would be microseconds actually.
Any microseconds.
Milliseconds sounds pretty high. Yeah.
But like, if that's small, we can assume that that's actually as a 0 time. Am I right?
Yeah.
So, okay, I see. So that's actually like from 0 to 1.75 millisecond, 1.7 second.
Yeah. But these are the centers of the windows. It's like the center of the summation of the windows. So it really, okay, I guess I can actually bring up the actual windowing. That might help.
Actually, before you do that,
Oh.
so the bottom left, the blue, you said that was the final result.
Sorry there. There it is.
So when you turn the system on,
Yes.
do you turn it on with the same ramp that you're turning it off?
I don't quite think that's fully controlled, so it won't be exactly the same.
Because it looks like, okay, there's a sort of an EM induction effect that's going on.
That's
right
from the TX, yeah.
At the beginning for the transmitter turning on.
Yeah.
You don't see that when it turns
But
off.
we don't when we see it turn off. This has been kind of a thing we've been seeing in the DVDs, is they just, and actually they were on our EM stuff too. There is the Phoenix transmitter, and they've got this, the start just does this weird effect like that, but you don't really see it in the off time.
So it's something that's kind of going on with the transmitter. You're putting something, ramping that thing up, and there's all kinds of currents in the transmitter or something, and you're actually measuring those effects. Whereas if the current is uniform now and you turn it off, things behave more straightforward.
Reliably, that's how we've been experiencing it. Yeah, the EM one was even more wild. It would be like half of the on time. You would see this huge just go, and it's like, well, we need that on time. But they have, I think they did put a patch in, so that is fixed now. But you still see a lot of this little transient at the beginning.
Do you have a name for that? I mean, it's one to sort of look up.
I honestly don't know.
Can I ask a couple more?
Oh, questions? By all means.
So what to move from blue to the black? Are you doing some windowing?
That is correct. Yeah. So I'm just going to move this over a little bit here, and you can see our windows, or the windowing right here. So when you look at that half stack right there, we are starting our, like the first window, the start of the whole chargeability decay calculation is at your 20, well actually this one we have 40 milliseconds before we start calculating again. However, I do the 40 milliseconds, but I also do an overlapping taper, so that works down to be your delay case. However, for the basic point here, you've just got to have your time from and time to. Two vectors that just give you your width of your windowing that you're going to do on that lower, or that second half of the
So that's pretty late. 40 milliseconds is like.
Yeah, but I'm overlapping by like 40-some%.
Yeah. So my point was like it's compared to like a typical EM. Types of like data. Well, 40 like that's the latest time channel, I guess. So it's pretty late.
Yeah. But you've got so much more time to work with here. So you're just using those and you're marching down, and it's kind of a logarithmic space. So your late ones get larger as they go.
Right, and you do like a trapezoidal for the time integration. How do you?
So the integration I use just like well, that's kind of when you just want to look at the code here. I've got the window weighting. So it's not quite a trapezoidal. I use similar to kind of what you were with the John Kingman's done with the Halverson stacking, just like an easy hanging window kind of thing.
Oh, okay.
So weight them, and then I overlap. In this case, I've been overlapping by 45 degrees, 45% into the other windows.
So what is the length of your filters here then? Like Well, let's say what you got.
Well, they're going to change for every window.
Right.
Because your windows are spaced differently, but they're sized to the space of the window, so that if you've got 45 degrees. I keep saying degrees. I've been working geometry yesterday. 45% on both sides.
Okay.
That's happening for every window.
And like you have some reasons why, and then like what is it?
Well, yeah, you can actually, if you want to see some, because if you use if you think of it, if you just use a trapezoid, just your rectangle, that's essentially kind of like a high pass filter. You're passing everything. Whereas if you start, again, tapering the sides and the weights, it's almost like a low pass filter is happening.
Okay.
So let's just change this down to 101 for its attenuation. So that's kind of bringing everything up on the sides. The taper wise. It's marginal, but you can kind of see down in here that we're introducing some noise.
Can you actually like just do like a no filtering? Like let's say we're just picking that value for instance, like
just picking the middle.
Yeah. Can you do that? Like
I haven't made that, but
can you effectively like changing the size of the filter? Let's say you change its filter size as 1.
Yeah.
Then I think
then you would just take.
Can you do that? Like just curious, like how bad it is, like if you don't do anything.
Oh, I didn't program that. Actually, I think if you go too low, it crashes. Let's try that. Let's just put in 1. Oh no, it doesn't work with that.
So can you just make it really small, like a 2 or 3, like just?
I think what I'm looking at is the length of the window, and if it's not the length of the window, it won't use it because it wants to at least give you the trapezoid. But I kind of like the idea of testing that though. Just putting 1 in. Yeah, indexing. Yeah, so it's trying to, it won't let you do anything unless it's the size of the window. It's happening right here.
Sorry, John, I think I may have deconnected partway back there. Can we just run back the plot on the right-hand side and then what you're doing?
Yeah. Let me just bring that up here.
So you've got uniformly sampled data and you're trying to put it into particular bins. Is that what you're doing at this point?
For the decay?
Yeah.
Yeah, so we have made windowing, I guess, or bins would be.
But he's still using the filtering, another filtering, like it's like a moving average, rather than like just integrating. But like when you integrate, you can use some sort of like special filters that like housing filters between intuitive.
So rather than just like averaging everything in the bin, we're applying a tapered window to average over that window.
Yeah, and it leaks into the other windows, so the other windows.
Okay.
So it's not just, that way it's a little bit more fair, so that this window at least gets some of that data weighted good, whereas the next one, it'll be on the back end of the taper. Makes sense.
Yeah. But if the goal is getting a really nice decay, let's say some decay, it's okay. Yeah. Like not a really especially like smooth decay. If that's the case, like what would you do? Like you still want to use that like a tapering windows and
if you want, or if you have one already, or sorry.
Well, like usual, I think the reason why you need that very smooth window, like a smooth function at the end, like now at the end of the day, you're going to integrate that where you want to have a single value and then invert for it. Like that's the goal. Yeah. But let's say if you want to invert for full decay to recover some chargeable parameters, for instance, then do you think are you going to do the same like a filtering here, or you may consider a different like a processing?
I don't know. That's a good question.
It's just curiosity,
because something like that, you improve the decay, like you add in or you fix the weights a bit more, and you get a smoother decay. But how much does your chargeability actually change? And then also, I guess I've written here a cold fitting cold fitting tool. And you can see that, okay, so with 101, we have, it doesn't really update very fast. Yeah, the chargeability is 4 from the cold fit curve.
Chargeability 4?
4 millivolts per volt.
Oh, I see.
Yes. Whereas I guess if we increase that back up to 401, I bet you the same curve will fit that, and you'll still end up with the same cold parameters. Yeah.
Yeah.
So if you're looking to extract the parameters, maybe prettying it up isn't so much necessary. But again, this is kind of a bad example because decays can get wildly bad, and by putting a little bit of effort, you can start recovering a nice natural looking curve. And there I could see the benefits of getting a better chargeability or a better C tau.
Because depending on what averaging window you apply, you're changing your frequency response, right? So if you use a boxcar, that's the same function in frequency, which if you have any noise is going to make a mess.
So yeah, it's just little, you don't have to do all these things, but they're just available. And yeah, it's something to play with. Again, this is kind of stuff that has just been developing, and you know, we've been finding some good results out of it, and yeah, why not share?
That's great. That's great.
Well,
so there's still a lot of testing that needs to be done per se, I guess. I've had a couple projects where it's actually been a tool that I've been able to use and was beneficial. But like you said, yeah, the goal is to just extract something that you already have, great data.
Right.
Is there a point?
So, okay. And how do you define your DC data here then? Like, let's say, okay, that's what you got.
Oh, okay.
IP data is in the off time, and that seems like an IP data that you may provide.
Yeah.
And how about the DC data?
The DC data, I have written just a little function here. Yeah, I don't have it printed, but it's just a little method is just get primary voltage, and then you just give it the stack, and it'll send out your DC. However, for any other, like if you want to start sampling the on time, I'll have to just fix a few things in the code. But yeah, should be all written. Or what are you looking for in the on time? Is your question?
Yeah. So okay, what I expected, I think from your on time data, I might just pick late enough time, and then maybe average like some time. I think that's what I thought. Like, I'm just curious, like how in the real world, how you guys actually define how like obtaining the IP data. I was just curious about that.
Okay. I think I'm still confused. Sorry. Just to go back to the DP thing, you're right about we just wait for the on time to be stable. If like right here, I go from 50% to 90%. So those are just my parameters, and then when I plug it into this get primary voltage, it just averages my DP in that window.
So for the DC, you're still taking a window of the on time. You're not picking like
not the point. Yeah, it's a window.
You're still taking
over half to 90%. Yeah. And then that one isn't tapered or anything. That's just a simple of the value, because ideally it should be stable. If it isn't, then yeah, I've got to talk to the people in the field to make sure things improve. So now you're wondering about the IP.
No, I think my question was just this.
Okay. Yeah. So other than that, no worries.
Okay. So when you actually have something there where you had get frequency, don't change it. Get frequency, but frequency is spelled different than we would do it.
Oh, I spelled that very wrong, actually. I have to improve my spelling. But yeah, that's the.
So would that? I mean, what would have happened if you tried to run that?
So that's what's plotting the frequency response in that plot, is using this function. So I change that to window 2, and it gives me the frequency response. Oh, I see.
So your initial object actually is spelled with frequency that way. It's not like you just
I spelled
something.
With different.
Yeah, that's a spelling mistake.
Okay, but consistent spelling mistake.
Yeah, consistent spelling
Yeah,
mistake.
okay. That's fine.
I am kind of notorious for things like that.
Sorry.
You might have to watch me.
We commit the inverse crime, so it's the same.
Nice. And then, yeah, so I've also got the tools to get the frequency response, phase response. Where do I have those in here? Kaiser windows. Weighted VS. It's in here somewhere. Oh, yeah. So anything you kind of want in a time domain IP should be here.
Yeah, that looks great.
I still, or my next move is I was going to do some of the frequency response stuff, like getting the harmonics from it. Or,
Right.
yeah. I was just going to talk about how to structure that, make that a kernel in itself, maybe. But, yeah, once I start on that, we'll get there.
Can you show me how are you doing? Like, you said you're using mappings.
Oh, okay. Yeah, right here. So let's go with the filter kernel, for example. So if we start up here, where's my filter kernel? All right, so I'm building the the shape there. So that's your window. So you make the shape, and then the THK here is short for tapered half kernel. Yeah, so you just simply make your object, your filter kernel object. And then when you do, like you guys showed me here, the multiplication, I fit it in right here. So when you make this object, it immediately makes the kernel. If that's the first thing it does, it's automated so that it's ready to go. So that when you do the multiplication, it's literally just taking that signal, making that matrix of all the half periods, and then multiplying together.
Okay.
And then it, just outputs.
I see.
I don't know, do you have to define both mols, R mol and?
What we've typically done is actually, and this is one thing we could play around with the structure a little bit, is use inheritance to deal with that. So we didn't, like, in the maps, you'll notice, like, if you look at any of the parametric maps or any of those, we don't actually, like, explicitly overwrite them all.
Oh.
We inherit that from the identity map.
Which has...
And so that, then we just take care of all of these details so that you don't have to rewrite them. So we used a method called def _ transform or something like that. And then as long as that's consistent through everything that's inheriting your base class, then we can just say that if we mul or R mul, like, do the same thing. And that's fine. So you don't have to repeat code as much. So I can show you that afterwards if that would be helpful.
Yeah, maybe they could put in there somewhere.
Yeah, because then too, you can do a lot of sanity checking on the base class and then just not have to worry about that later on.
Okay. I just don't think that this is necessarily, this might be the base class, technically, the filter kernel.
Yeah.
And then modify from there.
Yeah.
So maybe this would be like the identity map?
Yeah, I think there's a bit you might want to, we could lighten up so the base class is quite light.
Oh, so to make it actual, okay. I see.
Yeah, and then so you make it something that's inheritable and then go from there.
And then all these, so like the decay kernel, filter kernel, they'll be really light in a sense.
Yeah.
Compared to that base class.
Well, yeah,
So
yeah.
Oh, okay.
You sort of abstract the pieces that are common to everything.
Yeah.
Put that in the base class. And then
Then
only
variation.
implement the pieces that need to change.
Ah. Okay, yeah, no, that makes sense. I'll take a look at that for sure. Yeah, and then the decay kernel is built similar. You just set everything as it is, makes up everything, and then its multiplication, of course, is a little bit different because it's actually using that function I have down here, get weighted VS, and it just calls that for every window. That's pretty much what that's doing, what that mapping is doing. So, we can go up to it. Yeah, so it goes through all the windows, makes up the filter kernel for that proper size, weights them, spits it out.
Is it very easy to change your sampling rate? Like you're using, what is it, 150 per second?
Yeah.
like making that up to 10 kilohertz? Is that really hard, or like?
Would you like doing that
just
physically in the instrument?
Yeah. Not here, but yeah, physically in the instrument. Is that really hard? Or?
I don't know if it's necessarily hard. It's maybe more cost as well. I don't know if I have really an answer for that one, but it seems that they have. Yeah, I'm going to go with it's like the cost thing, because our engineer, we're asking him. It's like, oh, people are asking for higher frequency, and he bumps up to 200, and then it's like, oh, okay, well. But again, it is strictly just an IP unit, and I guess there really hasn't been any hard evidence saying a higher sample IP signal is more beneficial, I guess. In a sense. You would think it would be nicer for frequency domain, in a sense. Then you could have a lot better, or a lot finer sample frequencies. But, other than that, it just really hasn't been a push for it. I don't know if it's necessarily hard. It's just if it doesn't need to be done, they're not going to do it. Whereas, the EM side of things, that you got to start at kilohertz frequency. Yeah. Fortunately, that's all I can say for that.
No, I think that's great.
And the final thing here is I've been working with writing the coal fitting. That just shows what came out of the coal fit. So right now I'm just doing like a simple kind of lookup method. You give it an initial C tau, and then it just iterates through those. And then the search radius. So you can give it a big span or a small span, and then you can kind of define it or refine it if you need to.
Right. So it's a global search method?
Yeah, pretty much. Or in your defined band. So you give it an initial point to start with, and then you tell it to only search. Well, so I guess it's not entirely global, but just a minute.
No, but it's not a gradient-based method.
Oh, no.
You're trying to find some parameters. You're just trying to find a best.
Just the best fit. Yeah.
And then you're providing the parameters as well. And then is that useful for?
Well, I've been experimenting with it for errors. Trying to get some errors into the inversion just to see what it does, and if we can better the inversion instead of just using a blanket 5% or something like that. So far, things have been working out a little bit better. I think the errors are a bit high because, even this one here, it's saying 17%.
You're not fitting really well,
and you're not fitting super well. But would you really assign that a 17% error? That seems a little high. So this is kind of where I'm still working in this area to see how this can be improved. I did also implement with this coal, you can give it a weight as well. So say you just want to fit the end, the late time. You can just give it a weight where it's 0, 0, just give it 1 at the end. So then maybe you can, because I guess it was Maxwell, the EM software there, you can kind of give it your window or it'll tell you tau and whatnot. So I was kind of thinking you could do the same thing. I don't know if that's if that's something that people would do, but I just put it in there just to see if you wanted. Oh, maybe the ending is this certain tau different from the beginning. Is that something that would be useful?
Might be, and also just kind of interesting checks, right? I mean, the thing is, once you've got this, then you've got our own software. You try things out and experiment.
Yeah, and that's pretty much where I'm at with it. I just trying to figure out what to do with it.
Are you how do you compute the coin time domain? Are you using computing frequency domain and convert that into time? Is that what you're?
It is a time domain based one. I didn't write it. It is it's an old technique. Dennis handed me the paper a while ago.
But it's like a sum of.
I can't. I'm going to brutalize that name. But yeah, I've referenced it up here. It's in geophysics journals. It kind of uses some kind of weird triangular filter
I think I can. Okay, I got it. Yeah, so you're doing frequency domain first, and transfer that into
Also,
time.
it goes in the frequency domain?
I'm pretty sure.
Oh. I haven't put that in a while, yes. I do have a version of this that can be a bit faster. I've just noticed that NumPy does have the tiling functions. And that's what I used in my C++ code that made it really fast. So this one's still just using the for loop, but I know I can improve that there. But again, I've just kind of been making it to see what can this be? What could be made of this kind of thing?
Yeah.
And that's about all I've got.
It's a lot.
That's great.
Okay. I was hoping to have more done for you guys, but things got a little bit busy, and I've been playing around with the SimPEG forward modeling and inversion side of things.
Oh, how's that going?
I think it's working really well. Oh. I have a little problem with the 3D IP forward modeling.
Okay.
But yeah, I just ran it yesterday, and I had an error problem, and I stopped storing J, and then that fixed that problem, and now it's just like it's giving me like a expected something float and got this.
Well, we can check.
Yeah, I'll send it after another thing. But the 2D stuff was working great, and that was all I really needed to make everybody happy.
That's great.
Yeah, so I can push. I think you've given me privilege to push. I can push this up onto the processing, and
yeah, that'll be.
If you guys ever want to try,
that'd be great.
Tell me what I've done wrong and how to do it better.
That'd be great, and I can we can point out some stuff with the mappings and like give a couple of structured ideas there for that too.
The one thing I really wanted to ask a question about is in my stacking here, I still have to use a for loop because I'm building a matrix that the 3 diagonals are the weights essentially, or we're helping map the weights.
Right.
But I don't know a fast way other than using a for loop to put those in. Is there a way that you can?
Oh, I think you can just crop, like connect to that product, like
a CSI matrix.
Yeah, we can make that a sparse matrix. I think that part we could definitely help.
Okay.
Give vectors and then give diagonals and then all
then
stuff on the diagonals.
Yeah.
I knew I brought it to the right people.
But that depends, I think. So if you're actually forming the matrix, I think that's probably better.
Yeah. Well, let me just. Oh, that's a Decay kernel. Yeah. So it's around. So right here, I introduce the shape, and then these temps, and then the news. I'm really bad at labeling things, but it's just essentially mapping everything so that it knows what those indices are, and then I use the for loop to fill those indices.
But
so if we can clean that up by just using a nice little Chronic or anything like that, like it's already fast, but it never hurts to go faster.
One thing too, we might want to think about down the road is lightening the emit as well.
Oh yeah.
And saving a lot of those variables as keyword arguments, because then if you want to just like fiddle around with it in the notebook and like change your filter parameters and plot and sort of iterate in place.
Yeah.
Because right now what you would have to do is create a new filter for every time you want to change your parameters.
That's true.
But if you set them as keyword arguments, then you can go in and just change them, and allows you to play a little more.
Okay. Yeah.
So. Yeah. Something to think about.
Cool. Yeah. No, for sure. I like the techniques that you guys have already introduced, so keep on going.
John, can we access the window, your papers, like the hangings and all the other ones outside the class, or we need to instantiate the class?
No, that's what they're doing right now is you do them outside the class.
Okay.
And then you just send it to the filter thing. So yeah, it's just a simple call to.
So what's DCIP as well?
That's just my tools page kind of thing. So it's just calling from there. Just get me this handling window. Get me my Chevy jet and my Kaiser window are broken. I tried them up this morning. It's not working properly. My Bessel function, I think, is weird.
The THK was a matrix before, right?
THK.
Not here, but
before.
Before itself, the THK was a matrix.
That was.
And at the end of the day, you're just doing matrix vector plot.
Yeah. Yeah.
And you're doing the basically exactly same thing for all the location, all the data, right? Like
What do you mean by all data?
Oh, like this is one data. Oh, well, not data, one physical, like a receiver transfer.
Oh, yeah. So this is just the one. With our system, because it's the mesh network, sometimes they start later or start sooner than the others. So we can't quite treat it with the same filter kernel all the time.
Oh, I see.
We can force it, but if one got the message late and it's say half of the signal of the rest, we just force it to just make up its own stack and go with it.
Right.
So ideally, from say like a DDD instrument, everything starts at once because they're all interconnected by wire. So you can tell it, you can just make one filter kernel and go. Whereas, this one, our times can vary a little bit. So we try to keep it consistent, but again, when you have those little, or say you've got all of a sudden the node got kicked, and then you've got to take the last little bit of the signal so that you can at least get some data out of it.
So in general sense, like each location may have a different parameters of like stacking.
Yeah. So all the windowing, or say the decay windowing and all that, that's all uniform. It's just the filter kernel may change from site to site.
Nice.
Say like the last job that we were on, camels kicked every hour. There'd be like a ton of nodes and just got like a burst of noise everywhere. It's just like, It's funny, all the surveys are either up on the steepest side of a mountain or in the middle of a herd of water buffalo. Ridiculous.
And is there any challenges that you guys are up against in here, in terms of processing? Like, is there a big problem?
Just little things like that, because it's with the system, it's processing thousands and thousands of dipoles, and it's just you're trying to find that one that's throwing everything out, and so it's just kind of, I guess the hard part is automating, finding all these problems and these steps, and slowly making our way there.
And it's what you guys are doing. You've got one reference point, and then all the receiver location is connected to the reference point, I guess.
So everything is connected via a single reference. Yeah.
And this processing is done for
This is just for dipoles. Yeah.
So from reference to one dipole, and that's what data.
That's what this is doing. However, this data that I've used is this node and this short, and this node and this short, and then makes that data.
Right, and then after that, if you want, you can make more data, right? Let's say you did this and that, but now you can do that.
Yeah.
So how, and then you're using that decay curve, or a decay curve to generate those values, or?
Oh no, we just use the nodes. Just change the node or the signals. So this one records one signal, and then we subtract it from that signal to get that dipole, so that we can do it from anywhere.
So you do that prior to processing?
Prior to processing, yeah. So what I've done here is I've just used my tools that I was producing and building for just working with dipoles onward. There's a whole other step for our data. But that's the thing, is we provide the dipole data. We don't give them just the node data so that everything has to be built all over again. It's the actual signal that was used to produce that data. So even though our system does that, we still supply that dipole time series.
Well, I think the great thing about this is that it opens up, flexibility to just experiment with a whole bunch of problems. I mean, everything from just, you've got a really nice, clean time series, which is great, but easy to add noise to that, but just to see what happens, or also within the, in the airborne data, we're now concerned about, okay, how many repetition rates do you need, so kind of cycle through. I mean, you can make use of stuff like this, because it does all of the cutting things up and make it negative and add it to positive, and it's just, you can see that those would be really useful utilities, and then to experiment with maybe some of the filter factors just to see what what's important.
Well, the thing is, I've been really pushed into finding, like, to improving what we put into the inversion. Because now that with all this data, it's just like, you can't go through every single data point one by one. So, maybe automating this a little bit, and what goes better, but better goes into the inversion, better comes out, I would assume. So how can we make that happen with all our data? Because that's the other thing we're finding right now is, say we do a simple 2D survey and we have multiple dipoles. We're kind of processing them all individually. You can't just throw them all into one right away. Because things happen and then it's just too much data to look at. So we've kind of just parsed it into pieces, and we're finding that it's been more beneficial than just like, oh, they want 200 to 600 meter dipoles. Here, throw it in inversion, and then it's just like, oh, well, now what do we do? Something's not right here, but everything looks all right. But it's just finding a way to be able to make this data fit into the inversion better. The better data, better error assignment. What's it going to take?
So do you have other, it seems like you're using that code as a QC tool. For instance, like having some idea, okay, that the data quality is okay. Yeah. But is there any other ways that you guys are using?
That's the most effective one right now. Is that one? We've just got basic little rejections, give you a range of chargeabilities or a range of resistivities. I go by errors of the on time, or how well your signal is, how stable it is. But yeah, so far the coal one has given us the best automated response. Again, it doesn't give you, let's say, the best errors, but at least it'll see that decay that's going like this and that, get out of here.
Yeah, actually that's something, we haven't seen that on the plot you show, but are you able to also output for each point of the IP decay an error bar based on the stacking?
Oh, on the stacking, I do not have that on there.
Is that something that's possible? Or
it is possible, for sure. I'm just trying to think how to formulate that. So you're saying the error, when you're calculating the decay, each window, you're going to have a little error for each window.
Yes,
standard deviation. That shouldn't be that hard to put in, but it's not a bad idea.
Because that would be a good measure.
Yes.
If they're fluctuating too much, it's noisy.
Yeah. Look at it window based.
Same thing could be done, I guess, for when you stack all your periods.
When you use the stack, or you can trim out the stacks that are. So I would probably do that for when I implement the ensemble stacking. That would work really good right there. Instead of changing just a brute force stack, kind of what this one kind of is with nice filtering. Put that into the ensemble stacking, and that would produce some nice stuff. That would be something I'm working on next. But I haven't quite ready. But I'd like that. I'm going to write that down.
But you were suggesting that before the stack? Were you suggesting that before the stack or after?
Basically using the stack as a way to have an idea of your errors for each window of the IP decay.
Or even to assess the quality of your decay.
Right? Yeah, exactly.
If some of them have very high standard deviations, you have a lot of fluctuations.
Yeah.
This guy's noisy.
I think that would be nice for a nice refined, you run quick QC over it, and then that would be good to really narrow it down.
What was the
Sorry, Deacon, we're having a really hard time hearing you. I don't know where your mic is, or if you have headphones with a mic that you could try.
Okay. Can you hear me better now?
That's better.
Oh yeah.
Okay. Yeah, I also had a hard time hearing the Dom and the Thibault. So what was your comments for stacking?
Edicon, we were just saying that it will, with the stacking, it will be nice to also output a standard deviation for each windows to assess the quality of the data and of the stacking, or remove point if we have too much variation around the mean.
Okay, I see. Okay, I see. So for each gate, you find like uncertainty or like error bar based on the stacking. Like
yeah.
Okay.
Do you do that at all and get rid of outliers or bad points?
Just mostly, well, in 2D, it's just been visual in a sense. It's no automation, but since the automation, no, we didn't look at this. I did this with with the ensemble stacking that I wrote. I kind of just did the stability of the whole stack. I didn't actually think of looking. Yeah, it seems very intuitive now, but yeah, I didn't look at each individual time gates. But other than that, the cold fitting was how we were rejecting wild points.
Yeah.
Okay, so maybe another comment. So in general, how do you guys think of like the pre-stacking version? Instead of doing all the kind of like a stacking and just put all the data into inversion, and instead of the averaging in the data domain, and then let inversion take care of it.
You mean just having redundant data put into your inversion? Is that what?
Yeah.
Well, it's like putting the same point in twice, but there's different realizations.
Yeah, exactly.
I think that has been kind of we haven't seen that so much in the 3D, but in the 2D, I've kind of been noticing that the redundant data it might actually be causing problems at the very least. But it's kind of hard because I looked at a few examples and some have been pretty close values, so it shouldn't be a problem. But yeah, then there's some that are different or significantly different, and you kind of wonder, well, what happened right there? And then that's where we're seeing a bit of a problem.
But that could be used to help you decide what your uncertainties are, right? Because these are essentially repeat measurements.
Yeah.
And if you've got two values of repeat measurements and they're quite different, and especially if their difference is larger than whatever floor and percentage you've got, that's where you really have problems in your inversion because you can't decide what to do.
Yeah. Okay. Yeah, I was figuring that was happening, but using that as the KC. Nice. I like that.
Yeah, so right now the only hurdle is the computing cost. So it's very tough.
Well, building with the code that we had it wouldn't actually be that much more time. Like, you could put on another dipole size. You could probably put on another 2 dipole size without having to sacrifice that much processing time. Just to figure out the redundancy.
I'm still not sure that what you're suggesting is particularly useful or why you do it, because if you take the same datum, let's talk about a linear problem, right? You've got specific kernel function, and now you're basically going to repeat that kernel function twice, right? Yeah. And then you're going to, you're assigning a particular uncertainty to it, so it's Gaussian in each. You're handling twice the number of data. You should get 2 misfits that are consistent with your Gaussian. It seems to me that you could just use one datum and an appropriate standard deviation, and you'd be at the same position.
Yeah, I think in principle that's mathematically equivalent. Maybe it's more like just basically there's less chance of introducing like a bias from the filters, whatever, or like whatever stacking approach you're using. It doesn't sound like that big deal. I mean, I was just saying like, basically it's kind of like you don't even touch data. It's kind of like that kind of idea. You just.
But maybe what you're getting at, Dequan, and it is something that is important, and that is knowing the responses of any of the filters that are applied, so you can actually put that onto your forward modeling, and so that you're modeling the filtered response. I mean, we see that in airborne EM data where they've got filters that are applied. And if you don't know what those filters are, and you just assume that you've got perfect kind of data, you can have some problems. So in that sense, kind of knowing the explicit details of all of the things that are going on in your processing scheme, and finding what those response curves are and putting them into the inversion could actually have some practical importance.
Cool.
I would still be careful by just putting like the raw data and hold like the raw data in the inversion, because let's imagine we have like just like four realization of the same data point, but one of them is a big outlier. Like the data misfits squares error. So this outlier gonna have like a huge impact on your fit, and your fit gonna take something like really in between the 3 points that are really nice and this outlier. So this outlier gonna have like a massive weight because we square an already big error. So like even if you put several like same time the same data point in the inversion, I would still do at least one pass in the data to remove the really obvious outliers. Because you square the error, so
that's just gonna ruin it.
So there's another benefit. So a outlier in the data can be translated into the model update, which is kind of really weird. For example, most of the data requires this number to go up, but because of the outlier, so one realization needs this number to be go down. And maybe it's easier for us to put some sort of constraint in the model domain and say this number should go up. It shouldn't go below a certain value. Then so basically means this sometimes it's hard to identify whether it's really outlier or not. But if you're working with the data, everything in model domain, it may be easier to tell, okay, this number should go up, and this model parameter should be like, for example, below certain points. And whatever data is requiring this model update is the outlier. Anyway, it's not something we have to do, but just like maybe a different approach.
Yeah, for sure.
So we're just past 11, so we should wrap things up here. One quick question: is there Dieter puts in touch with another student in Edinburgh. He's interested in looking at anisotropy, so he wrote his own CSEM code that includes anisotropy, and is wondering if he can compare against SimPEG. So it's all built in, but I was wondering if anybody's actually got an example that uses anisotropy or has played around with that much. No? Okay. If there's anybody who's interested in just poking around, then let me know and I'll put you in touch with him as well. But if not, we can send him a few instructions and then he'll probably get in touch. So, right. Any other items, things?
John, that was great.
Yeah,
that's a lot of stuff, and there's a lot of potential there from the point of view of just a whole bunch of different kinds of time domains.
So I'm glad to introduce it because this conversation has to start somewhere. Like when we first started, it seemed like everybody was really like, keeping everything secret. They don't want to share how they process data, and it's like, no, we need to start doing better. And the way this is going to happen is starting discussion.
Yeah,
and I've got more. I just I'll slowly pick away at it. Whatnot.
Well, there's some typical stuff like removing harmonics.
Yeah.
And, I don't know exactly what is typical noises, and then I think that might be good to have those kind of examples.
Yeah, sure. I'll see what I can dig out here next little bit.
Yeah, and a little bit noisier data.
Yeah, that
really
one
clean.
was nice. I was just kind of scared that if Glenn watched it or something, he's like, you gotta make sure you got good data on there.
We'll keep it secret.
We'll just say this is Visser's data.
Deal. Well, thanks for having me.
Thank you, John. Thanks. Good stuff. Thank you so much, John.
Yeah.
See you, Big One.
Bye, Big One.
Bye.